All right, so get ready, because today we're diving headfirst into the mystery of dark energy. You sent in this really cool article from scitechdaily.com. It's all about this weird force that seems to be pushing, like, everything apart. It's pretty mind-blowing, honestly. And I gotta say, even the name dark energy sounds like kind of straight out of sci-fi flick.
It does, doesn't it? It really
Yeah.
kind of captures like the whole mystery of it all.
Yeah.
This unseen, unknown thing that's like shaping the universe.
Yeah, exactly. But before we get too lost in the darkness here, we should probably clear something up. Dark energy. It's not the same thing as dark matter. I know they're both some kind of mysterious and all, but
Yeah.
they're totally different. And trust me, they're both equally mind-boggling.
You're absolutely right. They're definitely distinct, each with their own challenges to our understanding of the cosmos.
Yeah.
But today, it's all about dark energy.
Okay, so here's the thing that really kicked off this whole dark energy hunt. For centuries, scientists thought that after the Big Bang, the universe's expansion would gradually slow down because of gravity, like, every pulling on everything else. Makes sense, right? But as it turns out, the universe had other plans.
It did. It did. And the discovery that the universe is actually accelerating, that was a complete game changer. It really shook things up, how we understand how things work.
Yeah, it's like throwing a ball up in the air, right? And instead of it falling back down, it just keeps going faster and faster. Something's pushing space apart, and that something is what we call dark energy.
Yeah, a very good analogy. And what's fascinating is this discovery wasn't like a sudden eureka moment. It was more like a gradual piecing together of clues, a true detective story spanning over a century.
Okay, a cosmic detective story. I love it. So where do we begin? Take us back to the beginning of this mystery.
Well, it all starts not with dark energy itself, but with the work of Henrietta Swan-Leavitt back in 1912. She was studying these fascinating stars called Cepheid variables.
Cepheid variables, aren't those the ones that kind of, like, pulsate, like they're breathing in and out?
Precisely. Leavitt was observing these pulsations very meticulously, and she discovered something remarkable. The longer a cepheid takes to brighten and dim, the brighter it actually eyes. It's like a cosmic heartbeat, revealing the star's true luminosity.
So it's not just about how bright it looks from Earth, but its actual, like, inherent brightness.
Exactly. That's called the period luminosity relationship. And it was a total game changer for astronomy.
Wow. And what's amazing? This discovery was essential. Because without a way to measure those, like, vast cosmic distances, we would have never figured out that the universe is expanding. So Henrietta Leavitt, way back in 1912, she kind of laid the foundation for one of the most significant discoveries in cosmology.
Absolutely. Her work gave us a cosmic yardstick, a way to actually measure those distances across space. But the story doesn't end there. Around the same time, another astronomer, Vesto Slipher, he was making observations that would further contribute to this puzzle.
Okay, so we've got Leavitt measuring distances with her Cepheid stars. What was Slipher up to?
Slipher was using a spectrograph to study light coming from distant galaxies. And spectrograph is like a prism, you see. It splits light into its different colors or wavelengths. Think about how a siren changes as an ambulance moves towards and then away from you.
Oh, yeah, yeah.
Light does something similar. When an object moves away from us, the light waves stretch out, shifting towards the red end of the spectrum.
So kind of like a cosmic Doppler effect for light.
Exactly. And Slipher observed that the light from many galaxies was shifted towards the red end, indicating they were moving away from us. This is called redshift.
So Slipher was the first to observe this redshift in galaxies, another crucial piece of the puzzle. That would eventually lead to the discovery of dark energy.
Indeed. And over the next few decades, scientists started connecting the dots. They realized that these seemingly separate discoveries, Leavitt's Cepheids, providing a way to measure distance, and Slipher's redshift observations showing galaxies moving away, they were pointing towards something truly remarkable. The universe was expanding.
Wait, hold on. The universe itself is expanding, so it's not just that galaxies are moving through space, but, like, space itself is stretching, carrying the galaxies along.
Precisely. And that's where our next set of cosmic detectives come in. Several brilliant minds, Alexander Friedman, George Lemaitre, they independently concluded that Einstein's theory of general relativity, which initially seemed to suggest a static universe, could actually accommodate this idea of an expanding universe.
Wow. So even Einstein's theory, which is like, the bedrock of modern physics, had to be reinterpreted to account for this mind-blowing concept of an expanding universe. But who actually provided the, concrete evidence for this expansion?
That credit goes to Edwin Hubble and his associate Milton Humason. In 1929, using Humanson's meticulous redshift measurements of distant galaxies and Hubble's work on Cepheid variables within those galaxies. They made a groundbreaking discovery. They found that the farther away a galaxy is, the faster it appears to be moving away from us.
Okay, I need to pause for a second and let that sink in. The farther away a galaxy is, the faster it's moving away. That's kind of counterintuitive, isn't it? Shouldn't things be slowing down after the initial, push of the Big Bang?
That's what makes it so profound. It implies that the fabric of space itself is expanding, carrying those galaxies along with it. It's imagine dots on a balloon that are getting farther apart as it inflates.
Okay, yeah, the balloon analogy, I get it. So this discovery completely changed our understanding of the universe. We went from a static, unchanging cosmos to a dynamic, expanding one.
Exactly, a complete paradigm shift.
Yeah.
And this relationship between distance and speed became known as Hubble's law, or the Hubble-Lemaître law, to be more precise.
Mm-hmm. So at this point, we've got an expanding universe.
Yeah.
And everyone's probably thinking, okay, great, mystery solved. But something tells me this is where dark energy enters the picture, right?
You're absolutely right. The story takes a dramatic turn in 1998. And this is where those supernovae you mentioned earlier, they come into play. Get ready for another plot twist in our cosmic detective story.
Ooh, okay, I am ready. Hit me with it. All right, I'm all ears. So what did these supernovae reveal? What shook up our understanding of the universe yet again?
Well, there were these two independent teams of astronomers, and they were studying these incredibly bright explosions. I call it Type Ia supernovae. They're cosmic lighthouses. They shine with this, very predictable brightness, which makes them super useful for measuring distances across the universe.
So similar to how Henrietta Leavitt used those Cepheid variables to measure distances, astronomers could use these supernovae as another cosmic yardstick.
Exactly. And these teams, one was led by Adam Riss and the other by Saul Perlmutter and Brian Schmidt. They're using these supernovae to track the expansion of the universe, right? But what they found, well, it wasn't what they were expecting at all.
I'm sensing another one of those the universe had other plans moments. So what did they discover?
They found that these distant supernovae were dimmer than they should have been, based on their redshift. Remember, redshift tells us how fast an object is moving away from us. And because we know the universe is expanding, we'd expect things farther away to have a higher redshift. They're moving away faster, right?
Yeah.
But these supernovae, well, they were dimmer than their redshift suggested, which meant they were even farther away than we thought.
Okay, so if they're farther away than we thought, doesn't that mean the universe is expanding faster than we initially calculated?
That's exactly right. And that's the bombshell. Instead of the universe's expansion slowing down, because of gravity, it's actually speeding up. It's like the universe hit the gas pedal instead of the brakes.
Whoa, okay, that is a major plot twist. So instead of the universe acting like that ball slowing down as it goes up, it's more like it got a sudden rocket boost. It just keeps going faster and faster.
Yeah, that's a great way to put it. It really threw everyone for a loop. And this discovery was so significant that Riess, Perlmutter, and Schmidt were awarded the Nobel Prize in Physics back in 2011.
Wow, a Nobel Prize. That definitely says something about how groundbreaking this discovery was. But let's get back to the mystery. If gravity should be slowing things down, what on earth is pushing the universe to expand at an accelerating rate?
That, my friend, is the million-dollar question.
Mm-hmm.
And the answer, as far as we can tell, seems to lie in this mysterious force we call dark energy.
All right, so we finally arrived at the star of the show, dark energy. But what exactly is it? Do scientists have any concrete answers?
Well, that's the biggest puzzle of all, isn't it? We know it's there. We see its effects in this accelerating expansion. But its true nature, it remains a mystery. However, there are some pretty fascinating theories out there, each trying to explain what dark energy might be.
Okay, I'm hooked. Lay it on me. What are some of the top contenders in the what is dark energy competition?
One intriguing idea is something called vacuum energy. Imagine space itself, even the seemingly empty parts, are actually teeming with activity. Virtual particles popping in and out of existence.
Virtual particles? That sounds like we're venturing into quantum physics territory. And honestly, my brain is already starting to hurt.
It is mind-bending stuff. But essentially, these virtual particles, well, they're thought to carry energy. And this energy could be what's driving the accelerated expansion. There's this constant underlying energy, pushing everything apart.
So empty space isn't actually empty. It's like a hidden energy reservoir fueling the universe's expansion.
That's the idea. But there's a catch. When scientists try to calculate how much vacuum energy there should be based on, quantum physics, the numbers just don't add up. They get a result that's either astronomically huge, like way more than we observe OR0, which obviously doesn't fit either.
So it's either way too much or none at all. That seems like kind of a problem for the vacuum energy theory.
Yeah, it's a significant challenge. This discrepancy is known as the cosmological constant problem, and it's one of the biggest head-scratchers in modern physics.
Okay, so maybe vacuum energy isn't the answer after all. So what are some of the other theories that scientists are exploring?
Another contender is something called quintessence. Imagine a fluid or a field that permeates all of space. But unlike anything we're familiar with, it would have this negative pressure, kind of like anti-gravity,
Yeah.
that counteracts the normal pull of gravity, causing space to expand faster and faster.
So instead of a constant energy, like vacuum energy, quintessence would be more like a dynamic force that can change over time.
Precisely. And that could explain why the acceleration of the universe doesn't seem to be constant. It might be changing, evolving over, cosmic timescales. There's even speculation that quintessence could be linked to dark matter, which is another one of those deep, dark cosmic mysteries we can explore another time.
Ooh, a dark matter deep dive. I'm putting that on our list for sure. But for now, let's stick with dark energy. Are there any other contenders vying for the top spot in explaining this mysterious force?
Some scientists propose that the answer might lie, not in a new type of energy or field, but in defects within the very fabric of space itself. Imagine like wrinkles or cracks in the structure of the universe, remnants from the chaotic early universe.
Cosmic wrinkles. That sounds like something straight out of a science fiction novel.
It does, doesn't it? These wrinkles, or cosmic strings, they could be creating unevenness in the expansion of the universe, leading to the acceleration we observe.
So it's not that there's like a new force pushing things apart, but rather the structure of space itself is wonky, leading to this weird expansion.
Exactly. It's a fascinating idea. But like all the others, it needs more evidence to support it.
Okay, so we've got vacuum energy, quintessence, cosmic wrinkles. These are some pretty wild ideas. But are there any explanations that are a bit more, grounded in what we already know about the universe?
Well, some scientists believe that maybe we don't need to invoke a whole new mysterious force like dark energy. What if the answer lies in our understanding of gravity itself?
Wait, are we saying that Einstein might have been wrong about gravity? I mean, his theory of general relativity has been tested and proven time and time again.
Not necessarily wrong, but perhaps incomplete.
Yeah.
You see, it's possible that Einstein's theory worked perfectly fine on, smaller scales, like within our solar system, but might need some modifications when we're dealing with, the vast mind-boggling scales of the entire universe.
So instead of introducing a whole new entity like dark energy, maybe we just need to tweak our understanding of gravity, one of the fundamental forces we already know.
Precisely. This approach is called modified gravity.
Yeah.
And it suggests that gravity might behave differently than we expect over, vast cosmic distances, leading to the accelerating expansion we observe.
Okay, so we've got this whole spectrum of theories. From virtual particles popping in and out of existence, to cosmic wrinkles, to rethinking gravity itself. It's incredible to think that we still don't know what's driving this fundamental phenomenon that's shaping the very fate of the universe.
It's humbling, isn't it? But that's also what makes this quest so exciting. We're on the frontier of discovery, pushing the boundaries of our knowledge, our understanding of the cosmos.
Absolutely. It's like we're living in a cosmic detective story. And the mystery is still unfolding. So with all this uncertainty, how are scientists trying to unravel the mystery of dark energy? What tools and techniques are they using to shed light on this elusive force?
Well, the good news is we're entering a golden age of cosmic exploration. There's a whole fleet of incredibly powerful new telescopes, both on the ground and in space, that are specifically designed to probe the mysteries of dark energy.
Okay, you've got my attention. Tell me more about these high-tech dark energy detectives. What are they, and how will they help us solve this cosmic puzzle?
Well, one of the most exciting is Euclid, a European Space Agency mission. NASA's contributing to it. It launched in 2023. And its mission is to create, a massive 3D map of the universe.
A 3D map of the universe? Wow, that sounds incredible. How is that even possible?
It's pretty remarkable. Euclid's designed to observe billions of galaxies over a huge portion of the sky, measuring their shapes and positions, with incredible precision. And by studying how these galaxies are distributed, how they cluster together, we can learn a lot about how dark energy has influenced the structure of the universe over billions of years.
So it's like taking a snapshot of the universe's history and using it to understand how dark energy has been shaping things, kind of behind the scenes.
Exactly. And Euclid isn't working alone. NASA's Nancy Grace Roman Space Telescope, set to launch by May 2027. It's also joining the dark energy hunt. It's like a superpowered Hubble, capable of capturing these incredibly wide-field images, which allow it to survey vast regions of the sky much faster than we can currently do.
So Euclid is mapping the structure of the universe, and Roman is going to give us this incredibly detailed view of how things have changed over time. It sounds like a pretty powerful combination.
Absolutely. And we can't forget about the amazing work being done here on Earth. The Vera C. Rubin Observatory in Chile, which is set to begin full operations in 2024. It's going to be scanning the entire sky every few nights.
Scanning the entire sky every few nights. That seems like a lot of data. What are they looking for in all that information?
The Rubin Observatory is going to be looking for subtle changes in the positions and brightness of billions of stars and galaxies. These changes could reveal the fingerprints of dark energy, showing us how it's affecting the movement and evolution of objects across the universe.
So we've got space telescopes mapping the universe in 3D, capturing wide-field images. And we've got these incredible ground-based observatories scanning the entire sky, all working together to uncover the secrets of dark energy. It truly is a global scientific collaboration.
And the best part is, it's not just big institutions and agencies involved in this. NASA even has a citizen science project. It's called Dark Energy Explorers, where anyone can help analyze data and contribute to the research.
Wait, seriously? So anyone, even someone like me who barely understands how to use a smartphone, can help uncover the mysteries of dark energy. That's amazing.
That's the beauty of citizen science.
Yeah.
By harnessing the power of, thousands of volunteers, we can analyze these massive data sets much more quickly and efficiently.
I love that. It's like we're all part of this cosmic detective story, working together to solve one of the biggest mysteries of our time. Now, you mentioned all these incredible telescopes, but what about the James Webb Space Telescope? Everyone's been talking about those, stunning images it's been sending back. Is it involved in the dark energy hunt as well?
Absolutely. While James Webb's primary mission is to explore the early universe, study the formation of the first stars and galaxies, it's also going to provide valuable insights into dark energy.
How?
By observing those distant galaxies in incredible detail, we can better understand how dark energy has influenced their formation and evolution over, billions of years. It's like looking back in time to see how dark energy has been shaping the universe from the very beginning.
So every new telescope, every new observation, it's adding another piece to the puzzle, helping us build a more complete picture of this mysterious force that's driving the universe apart. Are there any other missions we should be excited about in the coming years?
Definitely. There's SphereX, short for spectrophotometer for the history of the universe, Epoch of Reionization, and ISIS Explorer. It's scheduled to launch in February 2025.
Okay, that's a mouthful. What will SphereX be focusing on?
SphereX is going to create this massive map of hundreds of millions of galaxies, measuring their light in different colors or wavelengths. This will allow us to study the distribution of dark energy and how it has affected the expansion of the universe.
It sounds like we're entering a golden age of dark energy research. With all these incredible telescopes and missions, it feels like we're on the verge of some major breakthroughs.
It's an exciting time to be a cosmologist, that's for sure. With all this new data pouring in, we're hoping to finally shed some light on this elusive force that's shaping the destiny of the universe.
And it's not just about, understanding some strange force out there. It's about understanding our place in the cosmos, the grand scheme of things. It really makes you ponder the big questions, doesn't it? What do you think, listener? What's the most intriguing aspect of this quest to understand dark energy? Is it the mind-bending physics involved? The sheer scale of the universe we're talking about? Or maybe the philosophical implications of a force that's pushing everything apart?
It's definitely a question worth pondering. And here's another one to consider. If dark energy continues to accelerate the expansion of the universe, what does that mean for the ultimate fate of, everything? Will galaxies become isolated islands in this vast, empty expanse? Will the universe eventually be torn apart? Or is there something else, something we haven't even imagined, waiting for us in the cosmic future?
Whoa. Those are some heavy questions to end on.
Yeah.
But it just goes to show that the mystery of dark energy, it isn't just about understanding a force. It's about understanding the destiny of the universe itself.
Indeed. The quest to unravel the secrets of dark energy is one of the greatest scientific adventures of our time.
Thanks for joining us on this incredible deep dive into the mysteries of dark energy. Until next time, keep looking up and keep asking those cosmic questions.